Good day guys, this is Maneth Marilia from class A13 and I'm here to discuss two questions about two different topics in analytical chemistry. The first problem is about the applications of redox titrations and the second problem is about potentiometry. The first problem. This problem came from the book of The Fundamentals of Analytical Chemistry by Skoog, 9th edition, chapter 20, question 19. So let's analyze this problem first by identifying the given in the problem. So a 0.7120 gram specimen of iron ore was dissolved and passed through a Jones reductor. So it is clearly a mass of the iron there, so it's 0.7120 grams, and titration of the ferrous oxide produced required 41.63 ml of 0.01926 molar potassium permanganate, so that's a volume, so that 41.63 milliliters and a molar of 0.01926. This is what we need to calculate. Express the results of this analysis in terms of A, percent of iron, and B, percent of ferric oxide. The first thing that we need to do is to calculate the overall reaction. For the titration, let's write the equation for titration of ferrous oxide with permanganate. So let's balance that equation with acidic radium. So for our oxidation reaction, we have the ferrous oxide, and for our reduction reaction, we have the permanganate. We can see here that we have an oxygen atom, which make this an unbalanced equation. So we need to balance that. We will add an H2O with that. But again, we have a unbalanced hydrogen atom. So again, we will add 8 hydrogen atoms to balance the equation. Moving forward, we will now use that values in calculating the overall reaction. So as you can see here, the electron that was gained and the electron that was lost is unbalanced. So we need to multiply the oxidation reaction by 5 for us to get this overall reaction. So this is the balanced overall reaction. We will use this in our dimensional analysis. Next, let's calculate the millimole of oxidant, which is the permanganate in this case. So first, we are given off with the volume of potassium permanganate, which is 41.63 milliliters. And we need to multiply that to its molarity to get its millimoles. So we will end up with the answer of 0.80179 millimoles of potassium permanganate. So let's use that value to calculate for the millimoles of the Fe2 plus that reacted with the potassium permanganate. Now we will use the overall reaction that we got earlier. So it is clearly stated here that we need 5 millimoles of Fe2 plus when to react with 1 millimole of permanganate. So that's a relationship there. So we will cancel this out. Then we will end up with 4.00895 millimoles of Fe2 plus. Moving forward, we will now calculate the millimole of Fe2 plus in the sample. So the millimole of Fe2 plus earlier is the millimole of Fe2 plus in the titration. So now we will calculate for the Fe2 plus in the sample. So we are given off with 0.7120 gram of sample. So I just converted it with milligrams. So I will not be confused with the calculations later. So here we go. We have here the mass of the sample multiplied by the molar mass of the Fe for us to get the millimole of the Fe2 plus in this sample, which is 12.749 millimoles of Fe2 plus. Next, we will use that late, yes, this value. So this 4.00895 millimoles of Fe2 plus is the millimoles of Fe2 plus that reacted with the potassium permanganate. We will divide this value by the value that we got earlier, which is for 12.749 millimoles of Fe2 plus, which is the millimole of Fe2 plus in the sample. So we will divide those two, then multiply that by 100. Then we will now have our answer for letter A, which is 31.45% Fe in the sample. Next, letter B. Calculate the millimole of ferric oxide in the sample. So again, we need the mass of the sample, which is 712 milligrams of it, times the molar mass of the ferric oxide, which is 159.692 milligrams per 1 millimole of it. Now we have 4.458 millimoles of ferric oxide. Yes. Now, let's calculate the millimole of ferric oxide that reacted with potassium permanganate. Earlier, we solved for this value, the millimoles of the potassium permanganate. So 0.80179, let's multiply that by the relationship of KMNO4 and the Fe that we got in our overall reaction. So there you go. So here the millimole of KMNO4 will be cancelled out. Next thing that we need to do is that we need the millimole of the ferric oxide. So how many millimoles of Fe2 plus are there in the ferric oxide? So there's 2 Fe in Fe2O3. So there you go. We have now the millimoles of Fe of the ferric oxide, which is 2.004475. Let's move on. We need that value in solving for the percentage of the ferric oxide in the sample. So again, the 2.004475 millimoles of Fe2O3 came from the millimoles that reacted with the potassium permanganate. And here, in the titration. So at the bottom part, this is the millimole of Fe2O3 that was in this sample. So we need to multiply that by 100, and now we will get its percentage, which is 44.96% of ferric oxide in this sample. And now we're done with question number 1. Let's move on to question number 2. So, this question also came from the book of Fundamentals of Analytical Chemistry by Skoog, 9th edition, chapter 21, question 26. The Na plus concentration of a solution was determined by measurements with a sodium ion selective electrode. The electrode system developed a potential of negative 0.2462 volts when immersed in 10 milliliters of the solution of unknown concentration. After addition of 1 milliliters of 2.00 times 10 to the negative 2 molar NaCl, the potential changed to negative 0.1994 volts. Calculate the Na plus concentration of the original sample. So, let's now identify the given in the problem. So we have here the volume of the Na plus solution with an unknown molarity. We use 10 ml of that with an electric potential of negative 0.2462 volts. We added an NaCl solution to that. So the volume that was used was 1 milliliter of NaCl with a molarity of 2 times 10 to the negative 2 molar of it. Now, the potential was changed to negative 0.1994 volts. So these data are very important in solving this problem. Moving on, we have an equation that relates the PNA to the potential of the cell. So we have this formula. So what does this formula mean? Well, this P here is just the negative log of something. So PNA is just the negative log of NA. So the Ecell here is just the Ecell that was given initially, which is negative 0.2462. That will be our equation number 1. Now, the concentration of Na plus after adding NaCl solution. So, to calculate for that, we know that the molarity of Na plus is this one. So, we use 10 ml of Na plus solution with a unknown molarity plus the volume of the NaCl and the molarity of the NaCl. So canceling those values, we will end up with a millimole above or in the numerator. So below we have here the volume of the two samples, which is the Na plus and the NaCl. So we need to add that to calculate for the final volume of the solution, and we will end up with a ml below. So millimole over ml is just a molarity. So our Na plus, simplifying that further, we have this equation. So using that equation, we will now transfer that to the PNA or the negative log equation. So there you go. The Na plus there, we will transfer that one. So the E prime cell here is the second potential that we were given off, which is the negative 0.1994. This will be our equation number 2. Moving forward, we will subtract equation number 2 with equation number 1. Just simply as that. Now, we will simplify the left side of the equal sign by combining those in a single log form, and the right side we will just multiply those since we have the same value for our denominator. Solving for Na plus, yeah, then there you go, the simplified version of our equation. Simplifying further, actually you can put this already on your calculators and just should solve when you already got the answer. But for us to relate, or for us to understand the problem clearly, I will show you the step-by-step solution. Okay, moving forward, we simplify the right side of the equation and we transfer the negative sign to the right side. I mean. Okay, moving forward, we need to um, transfer the log there to the right side. So there is an antilog there. So antilog of negative 0.7905 is just 0.16198. So here we go. We're nearing the end. So we need to multiply the denominator to the right side of our equation, and then that will be that. We just need to isolate the Na plus here. Just distribute the 0.16198 inside, then you can already isolate the Na plus. Then the Na plus there, calculating further, we will end up with this answer. So this is the molarity of the Na plus solution. 3.5 times 10 to the negative 4 molar. So that's it, guys. That's the end of this video. Thank you so much, and I hope that I explained that clearly to you. Thank you.